Okay, let me get your attention, and we'll get started. All right, so in on CCLE, I've posted this document, and I guess we'll talk through it. And if you have questions, right now is the time to ask your questions, because after today, I will not answer any more questions about the final exam. Okay, so this is it. All right, so let me see. Okay, I think this fits. All right, so the final exam scheduled. It's in this classroom at the time that the registrar's website says. I think for this one it's Thursday at 3. I think. Okay. And so the exam's written for 2 hours and 50 minutes. That gives me a little bit of time to pass out the exams and collect them and all that. So anyway, you need a calculator. Absolutely, you need a calculator. Do not forget your calculator. You'll be in trouble, okay? Just make sure it's not your phone, okay? Or something that connects to the internet where there's a possibility of you talking to somebody else, okay? So any calculator is fine. Graphing calculator, that's fine. Scientific calculator, that's fine. Whatever, okay? You'll also need a ruler or straight edge, okay? Now please, if you don't own a ruler or straight edge, go to the store. You can go to Target and get one for like 50 cents, okay? Don't use your ID card or like the edge of your calculator or something. This is like, people have done this in the past and the things always come out bad. Like somebody just like tried to fold their piece of paper so that it has an edge. It was no good, okay? And then a pencil and eraser, so you can erase your wrong answers. Sometimes people will provide like multiple answers, and it's like I have to figure out which one they intended to be their answer or something. Just erase the wrong ones, okay? All right, so this is I'm going to list off all basically the questions that you will see, and that will be it. There's no surprises, okay? This covers everything that will be on the exam. And so this is what we got, okay? So you'll have some floating point arithmetic questions, kind of like the questions that showed up in homework 5. It'll be like, if you've got this many bits or whatever, and it's set up in this scheme, what's going to be the biggest number you can show, or stuff like that, okay? So review your homework 5 questions, and you can try playing around with like changing the number of bits and answering questions accordingly. And so you'll have a few questions there. You'll have a question that covers a numeric root finding method, okay? And it could be any one of these things, okay? It could be fixed point or Newton-Raphson or secant method or bisection method, okay? And so here's just an example problem. I actually didn't even bother graphing this, but okay, but yeah, I mean this will have a root, and so so I'll provide some kind of function. I'll provide a graph of the function, and I'm going to say find a root of this function, and if it's something like Newton-Raphson or whatever, I'll give you a starting point. If it's secant method, I'll give you 2 starting points accordingly, right? And then you will do manual iterations of this, okay? And I figure if you can do the algorithm manually by hand, it means you understand how it works, okay? Because sometimes when you do it just on the computer, the process is lost. And just so to kind of keep our calculation simple, you'll just round off your answer to 3 decimal places, and then you'll use your rounded answer for the next iteration, okay? Question? No, there's no cheat sheet or formula things, okay? Yeah, I don't. Yes.
Will the graph be provided for us?
Yes, I will provide the graph, okay? So I'll provide the function and I'll provide a graph. And then you will do your manual iterations, okay? And you'll, like, if it's Newton-Raphson, then you'll draw tangent lines on the graph and things like that, okay? And that's why you need the ruler. Okay? And so, you know, it'll be one of these methods that we've covered, okay? But yeah, no cheat sheets. You gotta kind of go through and make sure you know these things. All right, any questions on that? Okay, then you'll have manual iterations of a unidimensional optimization method, okay? And so those are either root finding applied to a derivative or the golden section search, okay? And so here's an example. If it's golden section search, you'll just use this, okay? Or it could be a root finding method applied to a derivative, which means, you know, I had a problem like this last time, and then someone complained that they didn't know what the derivative of sine was, and so anyway, I said you can't ask me that question. So anyway, oh, this should be indented, okay? You might have to just spend a little bit of time going over your 31A differential calculus, okay? So I won't go crazy, okay? It might be polynomial terms, basic trig. So that's going to be sine, cosine, tangent, e to the x or log of x, okay? And maybe products or quotients of those. So, you know those things, know your product rule, your quotient rule, your chain rule, okay? I won't do things like hyperbolics or you know, all of those other horrible things, okay? It'll be polynomial, basic trig, e to the x or log of x, okay? And that will be enough. But you can't be asking me how do you take the derivative of sine, okay? If you've forgotten, just go review your basic calculus. But you know, especially if it's root finding applied to a derivative, you got to be able to take the derivative, okay? All right, questions on that? All right. Okay, and then you'll have manual iterations of coordinate descent for a two-dimensional function. This is very similar to what you did in homework 5. And this one, I will provide a bivariate polynomial function, okay? So nothing weirder than products of, you know, a polynomial, right? Two-dimensional polynomial thing. I'll give you a starting point, and you will complete 2 iterations manually. So you'll update x1, then update y1, x2, y2. You'll start by holding one of those things. By holding it constant, it'll become a univariate function, and then you'll optimize it. And so for that, because it's just polynomial, just use calculus and figure out where d dx is equal to 0, right? That should be simple enough. Okay, and then update accordingly. And then and so you'll get like this little stair-step thing on your graph. So again, so there'll be a graph for you to graph these things. Okay, is that good? Any questions there? This feels okay. All right, and then you'll have a randomization test, and then a bootstraps test. So randomization test, I'll provide some kind of scenario along with the data. All right, and the data could be categorical, kind of like our Mythbusters yawning example in class, or it could be numeric, which is kind of like the parking lot data in the homework. And then I'll ask some kind of question. Is there evidence that a seed yawn increases the chance of a person yawning, or is there evidence that drivers take longer to exit their space if a person's waiting on them? Something like that, right? That requires a hypothesis test. And then you will write some code to perform a randomization test, okay? And so this is probably like 5 or 6 lines of code. It shouldn't be too hard. And you know, one of those lines needs to be how to estimate the empirical p-value, okay? Or find your empirical p-value. And then of course you can't actually run the code, but I'll say let's pretend this p-value comes back to be 0.23, okay? Then what kind of conclusion would you make, or something like that, okay? and you'd answer that. So this is also very similar to, I think, examples we've done in class or the things you've seen in your homework. Any questions on that? And then the last is bootstrap, okay? And so the bootstrap, same kind of thing, okay? Be ready to write kind of code for either parametric or non-parametric bootstrap, okay? And so the parametric, you would write like draw values from R norm or something like that. Yes?
Will you tell us which distribution?
Yes. So I think I write this right here. I will specify whether you will use parametric or non-parametric, and if it's parametric, I'll tell you which parametric distribution to draw from, okay? And if it's non-parametric, be ready to use either package boot or writing it yourself, okay, without package boot. Okay. And then, and similar to the randomization test, I'll provide a pretend p-value and ask what the appropriate conclusion is. Okay, questions on either of that? Yes?
This is somewhat unrelated, but will you post the video from Friday in the notes?
Oh, yeah. I'm sorry. Got busy this weekend. Didn't do it. Okay, I'll do that. Yes?
After the homework is due, could you post solutions or like somewhat version?
Okay, homework is due on Friday. Okay, all right. Remind me on Piazza on Friday night or something, okay? And then I'll post some, I don't know, partial solutions. I don't know if I want like the whole solution set out there, but okay. But I'll provide some stuff there. Okay? Yes.
Can you talk about how to interpret the p-value, and not the p-value, but draw conclusions from p-value?
Sure. Let me just wrap this up, and then I'll answer your question. Okay? All right. And then the last bit is there's just going to be a few conceptual questions about numeric and computational methods. Okay? So yeah, I don't want to like give away what question I'm going to ask on this part, but just for some idea, I could ask something like, when will Newton's method for root finding fail? Newton-Raphson method root finding fails. So it fails if the derivative doesn't exist, the derivative is equal to 0, or also possibly when the sequence of updated points ends up in some kind of loop, okay, which is low probability but not 0 probability. So that could happen, okay? Or another example, what has to be true about the data to use a randomization test? And what's that? Exchangeability, right? And maybe I'll ask you to explain what exchangeability means or something like that, okay? And so there's a few kind of conceptual questions related to these numeric methods that you should be able to answer, okay? And that's it. I promise no surprises, okay? There's no need to review things like scope or data structures from the first half of the course. The R that you need to know is the code that you will write for the randomization and bootstrap test, okay? So the code you write has to be correct. If you make mistakes in the code, you'll lose points. So that code has to be right. But other than that, you've already been tested on those concepts in the midterm, so I'm not going to test you again. I think with this information, you can write practice questions on Piazza and kind of test things out yourself. I think that's probably the best way to study, is to make up some problems and then see if you can answer them yourself. And I think I've given a pretty good description of these things, so you can expect. But that said, I'm not going to answer any questions about the final exam on Piazza, okay? I feel like this is a thorough enough document, so if you have questions about the final on Piazza, I'm not going to answer them, okay? And then for Piazza participation, I'm going to record that on Friday, and then I'm going to shut down the Piazza site on Wednesday, because the other class has their final exam on Wednesday, okay? So I'm going to shut it down then. So, I imagine some of you will study Wednesday night and stuff, but make sure you've consulted the Piazza before then, okay? All right. Questions? Is this good? All right. Okay. Yeah. This will be it. Okay. All right. Okay. So we had a question about how do we make conclusions with our p-values. Okay. So what is this? This is week 10, Monday. Oh my goodness. And then St. Patrick's Day is on Sunday. Okay, all right. I guess that doesn't matter, but hard to have fun when you have finals the following day. So, okay, week 10, Monday. Okay. Oh yes. Maybe I will just type this. Okay, rather than Okay. So what do we say? Why is this so small? Okay, so what was the question? How do we make conclusions based on the p-value?
And the alpha.
And the alpha. Okay. It's pretty warm. Okay. Is that big enough? How do I do this? 36. Okay. All right. So the simple answer is if the p-value is less than alpha, reject the null hypothesis. If the p-value greater than or equal to alpha, do not reject the null. Do we want a more complicated answer? Okay. All right. So if the p-value is less than alpha, okay. Well, first of all, what is alpha? Alpha is your significance level. And what does the significance level even mean in the first place? This is the probability of committing what? Probability of type 1 error, which is probability of, what's another name for the type 1 error? False positive, okay. I can't remember what I've told you guys already. So, okay, so false positive, so this is we reject the null even, I'll say we mistakenly reject the null when the null is true. And so our alpha reflects our willingness to make this mistake. Okay? And so why do we not just pick alpha equal to 0 or alpha equal to like 1 in 1,000? Because then we would not make a type 1 error, right? So why don't we do that? Huh? Right, because we would make the wrong mistake, right? So we do not pick alpha to be like 0, because if alpha is 0, what would happen? We would never reject the null hypothesis. Okay? We will never commit a type 1 error, but we'll never reject the null hypothesis. And then what's the point of doing a test in the first place, right? I could just tell you your answer, and that's gonna be, you're not gonna reject the null hypothesis, right? So like here, Okay, in general, reducing alpha, okay, or I'll say reducing risk of type 1 error will result in a higher risk of type 2 error. And so the type 2 error is the false negative, meaning the null is wrong, but our conclusion is not to reject it. Okay, so here's just an example. All right, so imagine we're in, I feel like I'd rather type this in Word than in OneNote. Oh my goodness, this is huge. All right, example, okay. So let's say we have a criminal trial, all right? All right, the null hypothesis. So in the United States, we always say defendant is presumed what? Defendant is presumed innocent until proven guilty, right? Which means, what is our null hypothesis? The null hypothesis is defendant is innocent. Alternative is defendant is guilty. Okay, so ideal world, all innocent defendants are acquitted. Okay, meaning they're let go. And all guilty people, all guilty defendants are convicted. How do you spell acquitted? There's a C in there. Okay. That's the ideal world. Okay. But real world, errors are made. Okay, what's a type 1 error? False positive, which would be, so innocent person is convicted, right? So either sent to prison, possibly executed, right? Depending on what the punishment is, right? Okay. Type 2 error. What's a type 2 error? This is the false negative. Right? A guilty person is let go. Okay, both are bad, right? We want to avoid both of these types of errors, okay? But the way our justice system is set up, we have said that the type 1 error is worse than the type 2 error, okay? So justice system is set up so that type 1 error is worse than type 2 error, right? It's the opposite of the Twitter conviction system. Okay, but this is what we have. So, and so therefore, if the type 1 error is worse than the type 2 error, do we want a big alpha or little alpha? Okay, so type 1 error is worse, so we want small alpha, okay? Because alpha is equal to probability of type 1 error, so we want, which leads to, we want to reduce type 1 error. Okay, that's what we have. Okay. Let's say, so in some trials, you know, the judge makes the decision and not a jury. And maybe the judge finds out later that, you know, he sent someone to prison, and it turns out that that person was innocent the whole time. They're exonerated by evidence later. And so the judge feels really bad about this and says, I never want to make this mistake again. And so I'm going to operate with alpha equal to 0, right? So then what happens? So that means the judge will never, the only way the judge can completely avoid making type 1 error completely is to never convict anybody, okay? And then that's no longer a judge. That's a get out of jail free card, okay? So so that's no good. And that's just the world that we live in that whenever you don't have all information, which is every day, always, all situations, you are at whatever decision you make, whether it's to choose something or not to choose something, you are at the risk of making either a type 1 or type 2 error, okay? And you just have to kind of think which one has the worst consequence, and you will pick your alpha accordingly. In the justice system, they do say use a small alpha, but not in those words. What do they say? Use a small alpha gets turned into what? Evidence beyond a reasonable doubt. Okay? Which means before someone arrives at a guilty verdict, it has to be beyond a reasonable doubt. There's a certain threshold, and it can't just be, I have a feeling that the person is guilty, or something like that. Okay. I guess the flip side, can you guys think of a situation where the type 2 error is worse than the type 1 error? What's that?
If you let a murderer go.
Let a murderer go? Yeah, I mean, that is bad. Again, both of these are bad, right? But again, but you're right. The way the justice system is set up is that we're trying to avoid type 1 error, and we're hoping that, yes, sometimes guilty people are let go, and we're just hoping that it doesn't happen often enough. But yes, letting a murderer go is bad. You know, letting I don't know. Here's a different scenario. Okay. All right. So a patient or a person shows symptoms of an illness. Okay. All right, and the person is not sure if he or she should, I'll just say they, singular they, okay, if they should seek medical attention. All right, so null hypothesis, person is healthy. Alternative, person needs medical attention. All right. All right, what's the type 1 error? And what's the type 2 error? So type 1 error is a healthy person seeks medical attention, right? And type 2 error is what? Yeah, a person who needs medical attention, who actually needs medical attention, does not get it, right? Does not visit a doctor. Okay. And both are bad, right? Type 1 error places undue burden on our healthcare system, okay? Wasting doctors' times. But type 2 error, what's the consequence of that? The person could get really sick and eventually die, right? And so we would say the type 2 error is worse, right? Could be fatal. Okay, so what do we, large alpha or little alpha? Okay, so we choose large alpha. All right, can you guys think of any website that operates with a large alpha regarding medical diagnoses? Right, so this is why we have the WebMD memes, okay, about, you know, anytime you type in a symptom, what's it gonna say? It's going to say, you're about to die, you need to go see a doctor, right? So, and the reason for it is because WebMD is operating under this set of conditions, okay? So, so WebMD will operate with a very high alpha to avoid type 2 error, okay? Because they would rather people visit the doctor and turn out that they're fine rather than the website says, oh, you're fine, and it turns out you actually have cancer or some kind of bad disease. But yeah, this is but you know, so we generally say, you know, the type 2 error is worse, so we crank up the type 1 errors. We choose a large alpha. But if it gets too large, then you get boy who cried wolf situations where you start ignoring the type 1 error, and then, or not, you've committed type 1 error so much that the effective alpha actually becomes 0. If that makes any sense, right? So you're operating with an alpha of like 20%, so that like everything triggers this thing, and you go like, I need attention, I need help, blah, blah, blah. And then it reaches a point where psychologically we've now turned that alpha down to 0, where we've completely ignored any rejection of the null hypothesis. So that's no good, right? And I think I read a story about burglars who did this. They like kept triggering some kind of motion sensor in a building, and so in the first 5 times it happened, the police would respond, but they I don't know, somehow they triggered the motion sensor so often without no one there, so the police would check it out and they'd go, okay, false alarm. They did this 5 times in a row. 6th time, the police didn't show up. They go in and they rob the place, or burglarize the place. So you know, don't get any ideas, all right? Okay. Anyway, is that okay? I don't know. Do you have more questions about this p-value stuff? All right. It should have been covered in your intro class. Yes.
Will you post the questions from lecture 2?
Okay, I'll post these up there. All right, I'll save this. Where do I go? Browse teaching 102A. Okay, let's get rid of this. Okay, we got a little bit of time. I wanted to do a couple fun things. I don't know if this is fun. This is my idea of fun, right? So there's something called kernel density estimation. I mean, if you guys heard of this, okay? This is a common thing. So let me just make an empty script. And you do something like x is our norm. We draw 100 values from the standard normal. And then normally you would do something like histogram of x. And then this is your plot of 100 values of this, okay? But instead, you might actually do density of x. Have you guys ever used the density function? And it prints something out like this. And then you can just ask, well, let's plot the density of x. Okay, and you get something that looks like this. All right, and so this is called a kernel density estimate. It's supposed to it's supposed to be a smoothed out version of our histogram, so it looks kind of like a probability distribution. Yeah. So this is our kernel density estimate. And so how does something like this work, right? How do we go from here to here, right? And I could just do this. So that's a different histogram, and here's the kernel density estimate. And obviously, with larger samples, we're going to get, so instead of 100, if I do 500, my histogram will look more normal. And then when I create the density plot, if there's weird artifacts in your histogram, then sure, they will also show up in your kernel density. But this is what we're getting, right? And so here is an exponential distribution, and it looks like that. And then if we create a plot of that, this is our density. Okay. Now, what's wrong with this density plot? Right. So what's my distribution? It's exponential, what's the domain of the exponential distribution? It has to be entirely positive, right? You can't have any negative values. But the density thing goes down below 0, right? So I could add AB line, what is it? X equals 0. Does that work? No, V line? How do I add a vertical line? Nah, never mind. Okay. Huh? Plot an AB line. X-intercept? Nah. All right, whatever. Okay. Just imagine a vertical line at 0. Okay. It's like I get the ggplot things and the base R, and all of this gets all jumbled in my brain. Life is hard, guys. Okay. All right, so you have the exponential distribution and things like this. I don't know, what else is a continuous? Oh, okay, so you have R beta. Let's specify. So here's your beta distribution, and that looks decent. If I do something like 1.5, 1.5, it looks like this, and it goes beyond the domains 0 and 1. Okay, but it's kind of trying to smooth out and give you something that looks kind of like a probability distribution plot. Okay, so whoa, sorry, my pen's all weird. Okay, so the way it works, okay, so kernel density estimation okay, this is a computational method to produce a graphic approximation of the underlying probability distribution. Okay, and it's basically just a more complicated histogram, because a histogram tries to do this exact same thing, right? A histogram is a graphic approximation of the underlying probability distribution. Okay, so it basically has the same intent as a histogram. Okay, but it's more computational, and really it's only possible because of the computer, and you get well, in a lot of situations, you get kind of these smoothed out plots, okay? Same intent as a histogram, but, you know, more computational and produces generally smoother plots. Okay, so how does kernel density estimation work? Basically, when you do a histogram, if you have an observation here and an observation here, the histogram will drop a brick at each location, right? So it's kind of like, so a histogram will stack bricks at the locations of data. Okay, so we kind of say how many data points are in this interval, and we'll stack that many bricks up on top of each other. Okay, so that's what a histogram does. What kernel density estimation does is it stacks, I don't know, mounds of sand on top of each other. Okay, at the location. Okay, stacks at the locations of data, okay? And you have options for the shape of the mound of sand. I don't know what the right word is, because it's when it lands, it stays and it keeps its shape. It doesn't like spread out like sand does. So I don't know. You're dropping these kind of these shapes that can stack on top of each other. But so you have options for the shape of this mound of sand, and so you know you can do rectangular. Probably the most common is the Gaussian. But you can also do, you know, triangular, and then basically an upside down parabola, which gets a fancy name. It's the Epanichnikov. Okay, it's I'm assuming a Russian guy. Okay. All right, so let me just kind of show what this is, okay? So x is going to be just that data points -1 and 1. And if I say make a histogram of x, it looks, that's not very good. Okay, but all right, we'll ask plot density of x, and under density of x, we can see this is kind of the result of one Gaussian centered at -1 and another Gaussian centered at +1, and where they overlap, those kinds of things have stacked on top of each other. Okay, and so that's basically what this does. And there's different options for the shape of the quote mound of sand. Okay, so one is the bandwidth. And I could choose something like 0.2. And this, so by default, R has a calculation method for what bandwidth to use, okay? If I do bandwidth 0.2, that's going to drop a narrower stack of sand, okay? And so this will look like this, and we can see the stack centered at -1 and the stack centered at 1. Okay, and as I increase the bandwidth, we can see these things get wider until they start to overlap. Okay, until a point where the bandwidth is getting quite wide, and basically when it gets wide enough, they kind of merge into one Gaussian-looking thing. Okay. But these are just, you're just dropping a stack here, okay? And again, I can kind of show you with bandwidth 0.2, and if I do shape equals rectangular, that was not. All right, what is the, that's not the option. By default, it's Gaussian, what is it? Oh, kernel. Kernel is rectangular, okay. Okay, so here is, it's dropping a rectangular mound of sand, okay? It's not actually, it's the rectangular, there's just ever so slightly, it's just a tiny bit trapezoidal, okay? Just a tiny bit, okay? So here is, you know, bandwidth 0.2. I'm gonna go ahead and increase this, and you can see they get closer. And then what's gonna happen when there's overlap? Well, let's see. When do they overlap? Okay, you get this thing, right? So you have the brick here and the brick here, and then just that little piece that overlapped kind of forms this little spike on the top. Okay, and it looks sillier and things like this. Okay, but visually, can you see what's happening? Right. So we're just so you've got these two rectangles, but you're making them wider, and so when they start to overlap, they form that thing. Okay. Let me just show you a triangular also. Okay, so we'll start off narrow. Okay, so here's one triangle, there's another triangle, and then, you know, we just get a little bit wider. Okay, so because one side is going down and the other side is going down, they level out, you kind of get this middle flat bar in the middle. And then let's go ahead and so you get this, and then you get this this interesting shape, right? Okay. Okay, and so you can kind of imagine how these two triangular shapes are stacking, right? So I do this with two data points so you can kind of see what's happening, but this is just happening at a much greater scale. You generally don't do density plots for two data points. You'll have like 100 points, and then you're just dropping 100 of these Gaussian shapes, or 100 of these rectangles, or 100 of these triangles on top of each other. And then, and it's not possible to do manually, but with the computer, all it's doing is just dropping these shapes, calculating where they all stack up, and you get kind of this smoothed out shape. So if I did the same thing with rnorm 100, so here's our density plot, and I can just do kernel equals rectangular. And so it's going to be a lot more jagged, okay, because you got all of these little rectangular things being added up, or triangular ends up actually kind of smoothing out because they have these smoothed out edges and stuff. And then the default is the Gaussian, which kind of smooths things out. But that also explains why for things like the exponential we get values less than 0, is because you're dropping, like if you have an exponential thing where the x turns out to be 0.001 or something, you're dropping this kernel shape centered at 0.001, and so you're going to get some of that mound of sand, which is centered at that data point, will fall into the negative side or fall outside of the regular domain of the data points that you see. Okay, so that's something that happens. But I think you know, you often will see kernel density estimates in the place of histograms and a lot of different things, and this is just kind of where it's arriving. It's just dropping these mounds of sand, but the computer just does all the calculations for us. Okay, we'll end there. We'll see you guys on Wednesday, and we'll see you then.